Section 2.6 exercises. First question asks us to find the domain of the quadratic function. And in this case, any value of x, which when substituted in will yield a corresponding value of y. So the domain is the set of all real numbers. And we can symbolize that by writing the open interval from negative infinity to plus infinity, meaning that any number x, when substituted into the equation, would give a corresponding output or functional value. Problem 2. Find the domain of the following function. Here we have focus on the denominator, square root of 24 minus 3x. Now normally, 24 minus 3x, what is under the square root, can be greater than or equal to 0. But since this represents a denominator, we have to have 24 minus 3x strictly greater than 0. Solving that for x, we'll take 3x to the other side. And dividing both sides by 3, we'll have 8 is greater than x. So the domain will be all values of x less than 8. We can symbolize this by the interval negative infinity to 8, not including 8. And all numbers chosen in that interval will yield a corresponding y coordinate out. Problem 3. Given a linear function and a quadratic function, find the algebra of each function listed below and determine its domain. This notation here means to take the function f of x and add it to the function g of x. So we'll simply write down our two functions, x minus 5, and then add that to our g of x function, x squared minus 1, and we'll add any like terms that we have and yield the result x squared plus x minus 6. Our result is a polynomial function, so the domain will be all real numbers for that. This notation says to take the function f of x and then subtract the function g of x. So we write down the function f of x minus, with the use of parentheses, the function g, x squared minus 1. We can then distribute the minus sign through the parentheses, minus x squared plus 1, and then we can add up any like terms that we have and write our final result to be minus x squared plus 4x plus x minus 4. And that also is a polynomial function, so the domain is again all real numbers. The last one asked us to multiply the function f of x by the function g of x. So we'll write down f of x and multiply that by g of x, x squared minus 1. Very carefully, we'll have to multiply this out. So x times x squared is x cubed. X times negative x is negative x, minus 5 times x squared, and plus 5 times negative 1 is 5. Add up any like terms if we have them. We do not, so we could simply rearrange it to be x cubed minus 5x squared minus x and plus 5. And again, that's a polynomial function, so the domain is all real numbers. Problem 4. We now wish to find the composition of functions, meaning to put one inside the other. This notation means f of g of x. Replace each x in the f function by the entire g of x function. So we will have 5 times g of x, 2x squared minus x minus 1, plus 6. Carefully distribute the 5 through. 10x squared minus 5x minus 5. Don't forget the plus 6. And then we can write our final result to be 10x squared minus 5x plus 1. The next asks us to compose the functions in the opposite direction. So we wish to take g of f of x. So we go to the g function, and for each x there, we replace it by the entire f function. So we'll have 2 times 5x plus 6, that will be squared, minus 5x plus 6, and then don't forget the minus 1. Okay, so first, using order of operations, we'll have to square out the binomial first. So if we do that, we'll have 25x squared plus 60x plus 36. Now we can distribute the minus sign through, minus 5x minus 6, and then minus 1. Finally, we can distribute the 2 through the parentheses, giving us 50x squared plus 120x plus 72. And then we still have minus 5x, and minus 6 and minus 1 is minus 7. And adding all the like terms together will give us the final result of 50x squared plus 115x plus 65. And that will be our final result for g of f of x. The last part asks us to find f of g of negative 1. And we already know f of g was found here. And this is the result. So taking that result and replacing x by negative 1 here, and the other x as well, replaced by negative 1 plus 1. Let's do out the resulting arithmetic. 10 times 1 plus 5 plus 1. 10. 5 is 15, and 1 is 16. And that's problem 4. Problem 5. Let's compose the functions f of g. So putting the g function inside the f function, we will have 4 divided by x. X is now the g of x function, plus 2. Okay. And to simplify this, an easier way to do it will be to multiply the whole fraction by x over x. And that will give us 4x in the numerator, and in the denominator, x times 1 over x is 1 plus 2 times x. Now find the domain of f of g of x. So the function we just found, we have a fraction, and the denominator cannot be 0. So first find the values of x for which the denominator is 0. So where 1 is equal to negative, where 1 is equal to, negative 1 is equal to 2x. So negative 1/2 is equal to x. So the domain will be the set of all x such that x is not negative 1/2. Or using interval notation, we can write negative infinity to negative 1/2 union negative 1/2 to positive infinity. And that's a fancy way to say x cannot be negative 1/2. Last question. Express the function h of x as a composition of 2 functions. Okay, so we can take f of x to be the function square root of x. We'll call that the outer function. And then we can write for the inner function, new one, g of x, which is what is underneath the square root, x squared plus 5. So if we take f of g of x, that means to put g of x inside the square root, and that will give us the square root of x squared plus 5, and that is the original function h of x. And that concludes section 2.6 exercises.